Okay, now this is the second part of the probability chapter, which is chapter 5, and I finished the previous audio, with these formulas. Now, in fact, I mentioned in there that there is a shortcut formula, so let's let's start from here. Now, before I go to the shortcut formula, I need to explain to you that I kind of changed the variable here in the previous audio. I had it as x, but here I have it as little r, because this is a new slide that I put, not one which came from the textbook, and I could not find the font for little x. So r here is the same as little x in your textbook, okay? And then what is r? R are the possible values that x can take. Now, in the previous example that we were talking about, where x is the number of heads, if you were to toss a coin 3 times, the little r values are 0, 1, 2, or 3. Okay, because there can be no heads, exactly one heads, two heads, or all three heads. Okay, so r are the possible values that x can take. X is uppercase X, or yeah, the big X is used to denote a random variable, and the specific values that the big X can take are denoted by little r here, and in the textbook it is little x. Okay, so they are pretty much the same. Okay, so now this is the formula for the mean, this is the formula for the variance. Now, rather than keep on subtracting, it's much easier to work with this formula, so you can find the variance also using this formula. So here you are summing r squared times PR product. Now PR, by the way, is this probability that x equals little r. Okay, and then you get that sum, and then you subtract the mu squared from that sum. Okay, so let's go to the next slide where I explain by means of the example here. Um, okay, so the example is the same: x equals number of heads when a coin is tossed 3 times. Uh, and r are the possible values. Now, as I said, little p within parentheses r is probability that x equals r. So the possible values for x, the big X, are 0, 1, 2, 3. And what are the associated probabilities? Right here, 1/8. 1/8 is the probability that there will be no heads. 3/8 is the probability there will be exactly one head. Okay, because there are altogether 8 outcomes. Out of them, only one will give you no heads. Okay, so that is how you calculate these probabilities. And then now to get the mean value, you need to get the product. So here I have in this column r times PR. So you multiply this by this and you get this. And when you add it up, you will get the mean value. So the mean is 12/8, which is 1.5. Now, how do you interpret the mean? What it says is, on the average, if you were to do this experiment over and over, that means toss a coin 3 times, you will expect about 1.5 most of the time, 1.5 heads. It does not make sense, 1.5 heads, but that is usually what is done. You will report the mean value to be the exact calculated value, even at times when the mean is not a real number, but is an integer. So what the reader or the user should do is use a little common sense and say, okay, the mean value is between 1 and 2 here. Okay, so that's the interpretation of the mean. And then to get the variance, now look, this sum, you need to first find the r squared for this sum. R squared means you just square the r values. So 1 squared is 1, 2 squared is 4, and so forth. Then you multiply r squared by PR to get this column. And then when you add it all up, you get this first term, the first term here. Okay. Now the first term is actually 3.0 minus, and then mu we got to be 1.5. So 1.5 squared, we'll simplify to get 0.75. Okay, so I'll just pause a little bit for you to understand. So summation r squared PR is what you get when you add all these numbers, and that would be 3.0, and then minus mu is 1.5, so mu squared is 1.5 squared, and when you do the subtraction, you will get 0.75, which is the variance, and the standard deviation is the square root. So you get the standard deviation to be 0.866. Okay, so, and remember the connection between the variance and the standard deviation. Standard deviation is the square root of the variance, and standard deviation has the same units as the random variable x. Okay, um, so now let's go to the next slide. So here in this slide, this is an illustration of how you calculate mu and sigma squared. And then let's go to the next one. Now in here, uh, you know, remember we talked about PMF. PMF stands for probability mass function. Now graphically, if you were to have the probabilities in a graph like this, then PMF is actually this area. Okay, area for x equals 2, x equals 1. Typically the horizontal width is scaled to be 1. So all that matters is, okay, PMF is actually the probability value. PMF, the probability mass function, is the probability that x is exactly equal to that particular value. So in here it is 2. So probability that x equals 2 is 0.2109. Okay. So in fact, here's a little bit of abbreviation here. AUC is area under the curve. This idea will come up in the next slide as well. Now let's go to the next one. In the next one, we are talking about cumulative probability. Cumulative probability means you add up to a point. See, notation wise, it is probability that x is less than or equal to a certain specific value. Okay, so it is kind of like the left tail. If you think about this whole thing as a spread or a big picture, this is the left tail. Okay, so probability that x is less than or equal to 2, for example, would be you need to add the probability that x equals 0, x equals 1, x equals 2, and that when you add it all up, you get 0.2617. Now this is the cumulative probability of 2. So cumulative probability, in fact, has typically it has notation to be CDF. Let's see. Yeah, let's wait for later. So for the notation, so cumulative probability means you add from the starting values up to that point. Okay. So likewise, probability x less than or equal to 3, you can figure it out. To this 0.2617, you need to add this probability, which is about 0.4 something. In fact, you can get it from a previous slide, the exact value. So when you add 0.2617 to this probability value, you will get the answer here, which is the cumulative probability for 3. Okay? All right. So this will come up later, the idea of cumulative probability. All right. Okay, so the next slide, we are starting to talk about continuous random variables. Now, so far, all that we have been discussing is in terms of has been in terms of discrete random variables. That is, discrete random variables is pretty much count data. They are variables that can take specific values. Now, continuous random variables, they can take any value in a given range. Okay, so it forms a continuum of possible values. Okay, now in fact in the next slide they have a spinner illustration as a continuous random variable. Using a spinner, what the random numbers it generates. So each the random number values will be a continuous random variable, because any number between 0 and 1 could be a random number. Okay, in the way the spinner generates the random numbers. Now other more real life examples are weight, height. You can tell me lots of stuff like temperature and so forth. Any particular measurement that can take a value in a given specific range, which no breaks at all, would be a continuous random variable. Okay, all right then. So let's go to the next slide. Here, in fact, is the spinner. So we know when you spin, this pointer will, point to a certain value. So it can be any value, in from 0 to 1. Okay, so it is see the random number value can be any value. So it is any number between 0 and 1. You know, so that means, the random number values will be a continuous random variable. Okay. Now, when you talk about continuous random variables, there are differences, okay, especially when you're talking about its probability, okay. First of all, there is a notational difference. Now remember, in the discrete random variable, we talked about PMF, probability mass function. Mass is like, because it is concentrated on specific values that X takes, okay. Like in the example we did, number of heads, you can find the PMF for X equals 0, 1, 2, and 3. For any other values, PMF is 0. Now PDF, when you talk about the PDF, it's actually for a continuous random variable, and PDF is used to express the probability that X is in a given interval. See, when you talk about continuous random variables, it does not make sense to talk about probability that a continuous random variable X is specifically equal to one particular value. Like, for example, probability that X equals 3 if X is continuous is 0. Okay, but for a discrete random variable, this probability that X equals 3 is non-zero. This can take a specific value, like what we saw in the discrete case with number of heads. Probability that X equals 3, which is all heads, was 1/8. So that can have a non-zero value. But for a continuous random variable, probability that X is exactly equal to any specific value is 0 always. I have capitalized always, and this is for any value. Even if you take height, let's talk in terms of maybe birth weight, okay. Now a baby can weigh, at birth, baby can weigh about maybe 8 pounds. But see, it is a continuous random variable, so it does not make sense to say that probability that the birth weight is exactly 8 pounds. You will always talk in terms of ranges. It's between 8 to 8.1 pounds, like a range, because continuous random variables can take any value in a given range. Even if you say that the baby is weighing 8 pounds, it's not exactly 8 pounds, because that's what we can do. That's what we can measure using the balance. Okay. All right. So this is an important result to remember. In fact, in the next chapter, this will come in next two chapters. Actually, this will come in useful. For a discrete random variable, the probability that X is equal to a specific value can be non-zero, but for a continuous random variable, it is always 0. No matter what the value is, probability that X is equal to little a is 0. A can be 1, 15, 95, 0.5, -1, anything. Okay. All right. So that is one distinction between discrete and continuous. Now also I said that PDF is used to represent the probability that a continuous random variable is in a specific interval. So here's the next slide which illustrates that. So if you want to sort of say, okay, the probability that X is between 0 and 0.5. See, these are the particular values or specific values that a random number can take. X can be any value between 0 and 1. Okay. Now this is the probability distribution. Okay. Now because it is random, every value has equal chance. Okay. So now probability that X is between 0 and 0.5 is expressed in this area. So this area under this curve, which spans this range, which is given here, would be the probability. Okay. So that's pretty much what you need to remember when you talk about a PDF. It is the area of the curve, okay, of the probability curve for the specific range that you are interested in. All right, let's go to the next one. Now here examples of PDFs. These are like different shapes of continuous random variables. The most common probability distribution function is the normal, the bell curve. We will study this in detail later. Okay. Now, the total area of any of these PDFs will be 1, because if you take a random variable, x has to be somewhere in the specified range. Okay, so that is one other property you need to remember. Total area under a PDF curve will be equal to 1. Okay, now also when you talk about area under curve, I mean, this here we are talking about the total area. Now for a specific range, or at least a part of the range, area under curve will give the probability that the x will be in that specific range. Okay, let's see. I think there's a illustration in the next slide, like in here. So in here, area under curve, like uh, this like darker shaded one is the probability that x is in the range up to 9. So probability that x is less than or equal to 9 is the area under curve with the darker blue shade, and it's approximately 40%. I mean, by using this formula, of course, it's we don't need to know that, but by using the formula, you can figure out that it is about 40%. Okay. Now, here's another important thing. When you talk about continuous random variables, it doesn't matter whether you use less than or less than here, or less than or equal to when you specify a certain range. The probabilities are going to be the same. For a continuous random variable, probability that x is less than 3 is the same as x is less than or equal to 3. You know, why the reason is, because see, what is the difference between this and this? This contains 3 in addition, but probability that x is exactly equal to 3 is 0. That's what we talked about earlier. So because of that specific property of a continuous curve, continuous random variable, less than inequality and less than or equal to inequality range, they both have the same probability. So the same is true even if you have greater than and greater than or equal to. Okay. Now remember, this is only for continuous random variables. For discrete random variables, x less than 3 and x less than or equal to 3 is different, because this has this additional 3. Okay. For the discrete case, it is different, but for the continuous, it does not. The probability wise, it does not make a difference. Okay. In fact, we will be using that idea later on when we study bell curves. All right. So let's go to the next one. Okay. So now, now in here, starting this slide, we are going to talk about probability rules. First of all, we need to understand the idea or the concept of conditional probability. Okay, so let me first of all go over the notation. So when you talk about a conditional probability, what you are saying is, okay, here you have two events, B and A. You're talking about the probability of the event B given that A has already happened. That means we know that A has happened. Under that condition, what is the probability of B? Okay, so that is what conditional probability is. Now, of course, there is a formula which connects the conditional probability with the joint probability. This is the probability that A and B both happen. Now, to get the conditional probability of B, given that A has happened, you need to divide the joint probability by probability of A. Okay, this is a formula. In fact, at the end of this presentation, I have written down all the formulas that we need to use, and this will be one of them. Now, let's in fact understand this idea of conditional probability by means of this example. Say you roll a dice and then say A is the event that you saw an odd number. Okay, so odd number means it has been either 1, 3 or 5. And B is the event that the number is less than 4. Oops, I should put less than or equal to 4. Okay, so here's a mistake. Less than or equal to 4. Okay, so B will contain either 1, 2, 3 or 4. Okay, now what is the probability that probability of B happening, given that we know that odd number has been observed. If someone tells, okay, someone rolls the dice and then, okay, he or she sees that it's an odd number. So that person tells, okay, hey, it's an odd number. So what's the chance that the number is going to be less than or equal to 4? You know that, only these three are possible. So there are three possibilities, and out of these three, what will favor this event less than or equal to 4? Only 1 and 3. So there are only two events favoring this particular event under this condition. So the probability will be 2 over 3. Now let me in fact put one more here. Um, probability of B unconditionally is equal to what? We do not know whether the number observed was odd or even. So altogether there are 6 of them. Out of them, 4 out of those 6, 4 will favor this event. So it will be 4 over 6. Okay. Um, um, Now that again turns out to be the same, which is actually 2/3. But typically you will not get the same answer. Okay. All right. So in fact, we will talk more about this, in another slide. All right. So okay. Now let's go to the next slide. Now, okay. Now that we know about conditional events, we need to understand what independent events are. For independent events, the joint probability will be equal to the product of the single probabilities. Okay. Now, what is meant by independent events? For independent events, the conditional probability of A given B is the same as the probability of A. What this means is the fact that B has happened is not going to play a role in determining the probability of A. Probability of A is the same. It doesn't matter whether we know that they has happened or not. Okay. So in such situations, you will say A and B are independent. So for independent events, the conditional probability is the same as the unconditional probability. Okay. And of course, you can, interchange A and B and write the same equation for B given A. Okay. Now, dependent events are events that are not independent. That means they are in certain ways related to each other. Okay. Now, if you talk about dependent events and if you want to find the joint probability, you cannot use this. You need to use this. This is the rule for dependent events when you have to find the joint probability. Okay. Of course, you can swap A and B and then get this part. Okay. Now, let me again give you another example of independent event and a dependent event. See, look, let's take the two events. The A to be College Park July 4th fireworks starts at 8 p.m. B is the event that LA will have snow in August. Let's use common sense. Are they going to be dependent on each other? No. So it doesn't matter whether July 4th fireworks will begin at 8 at College Park, for LA to have snow in August, right? So these two events are independent. So probability that B given A is the same as probability of B. It doesn't matter, whether the fireworks was going to start at 8 or 9 or any other time. This probability that LA will have snow in August is not going to change. It's the same for if you change B and A or like swap them, you will know that, okay, probability that July 4th fireworks will start at 8, will not be impacted by LA having snow in August, right? So now in a situation like this, when the two events are independent, to get the joint probability, you can multiply the unconditional probabilities. Just probability of A times probability of B. Okay. Now, if you do not have this fact, if your common sense does not tell that, okay, these two events are are independent, or it is not mentioned if you do a problem. Okay, you need to think of them as dependent events. Now the idea of dependence is very, very crucial. Let's look at this situation. A is the event that grandma has breast cancer. B is the event that granddaughter has breast cancer. What do you think? Are these two events independent? No, because we know that, okay, breast cancer is kind of hereditary. So if I know a person, a granddaughter whose grandma has breast cancer, I will say, okay, the chance that that person will have cancer would be much higher than any person whom I choose. So the probability, if you have a person whose grandma has breast cancer, that person's chance of getting breast cancer is higher. So the fact that we know this additional information, okay, change the probability in this particular case, but here it did not. Okay, now the third rule is about the or event. This is the event that either A happens or B happens. It's different from this. In here, A and B both should happen. Okay, here one of them, it's either A or B should happen. Then you will get this or event. Okay, now to get the probability of A or B, you can use this equation. Okay, now how do you get the joint probability? If you know that the events are independent, you can multiply the two probabilities. If you do not know them, you have to use this, which involves a conditional probability. Okay, now if the two events are disjoint, then the A and B probability will be 0. That means they do not have common events, right? Then you get probability of A or B to be probability of A plus probability of B. Okay, so when you use these rules, you have to sort of pay attention to whether events are independent or not, and also whether events are disjoint or not. Okay, these are not really difficult ideas, especially like, in this class, we are not going to do very complicated problems, but it's important nevertheless to understand these ideas. Okay, as like in biostatistics, now this kind of example is, even if you become a physician, or a social worker, these kind of ideas, about would be important. Okay, all right, let's go to the next slide. um yeah, okay, so here again, this is called the general rule of multiplication. So this slide is actually pretty much repetition of what was done before, and then like in the previous slide, actually, and then this is like an the same thing. Of course, probability of B is expressed in a little bit more complicated way, but I really do not expect you to know this. Second equation is optional. You can sort of figure it out if you like, or if you really, I'll be happy to sort of discuss this with you if you want to. But for this course, you don't really need this. Okay, all right. Now, what I did here in this last slide is to put together the formulas that you need. So here's the mean, here's the sigma variance, and here's the or event probability formula, and then here are the and event probability formulas, and then if the events are independent, you can multiply them together. Okay, so this will be pretty handy for the exam. I think I will put this slide in the exam one folder, but you can even use it. You can have it open when you do the exam. Just to remind you, all exams are open book, so you can look at all this stuff as long as you finish the exam in the specific during the specific time, which for midterms will be 1 hour. Okay, all right, take care. I'm finishing this chapter now, but there is one more to come for probability. Okay.